Change of momentum and impulse. From Newton's second law we know force F equals mv minus mu divided by t, or mv minus mu is equal to F times t. But the impulse of a force is equal to the change in momentum of a body, which is caused by the force F. This is also equal to the magnitude of the force multiplied by the length of time the force is applied. So, impulse can be defined as impulse equals F times t, or impulse equals change in momentum equals force times time. Impulse is measured in newtons per second, or ns. A good example of impulse is the action of hitting a ball with a bat. Though the contact may seem instantaneous, there actually is a short period of time in which the bat exerts a force on the ball. The impulse in this situation is the average force exerted by the bat multiplied by the time the bat and ball were in contact. It is also to note that impulse is a vector quantity, pointing in the same direction as the force applied. Now, let us consider Newton's third law. It states, for every action, there is an equal and opposite reaction. The upward movement of a rocket is the reaction due to the exhaust of gases downwards. With the action of a rotary garden sprinkler, explain how the third law is applied. Conservation of linear momentum. This states that when two objects collide and there is no external force acting on them, the total momentum of the objects before collision is equal to total momentum after collision, or we say that the momentum is conserved. In collisions between two objects without an external force, Newton's third law implies that momentum is always conserved. Collisions in which the kinetic energy is also conserved, that is, in which the kinetic energy just after the collision equals the kinetic energy just before the collision, are called elastic collision. Collisions in which the kinetic energy is not conserved are called inelastic collisions. If the two objects stick together after the collision and move with a common velocity, then the collision is also said to be inelastic. Experiment. A. To find the speed and acceleration of trolleys using ticker timer and tape. B. Using the collision of two objects to understand the principle of conservation of momentum. Apparatus. Ticker timer and tape. Suitable low voltage AC power supply. Trolleys. Runway or ramp. Diagram of apparatus. One important component of the apparatus is ticker timer. The ticker timer is used to measure time by counting dots made by it at specific intervals of 0.02 seconds. The main components of the ticker timer include a coil, magnet, vibrating arm, carbon disc, and tape. Let us understand the principle of operation of the ticker timer. The ticker timer consists of a coil which is connected to an alternating current, AC, supply, of frequency 50 Hz or 50 cycles per second. This coil is wound on a metal strip. The metal strip passes through a permanent magnet. Due to changes in the direction of the alternating electric current, the metal strip is made to vibrate up and down 50 times per second. This vibrating metal strip hits a paper tape connected to a carbon paper disc, which allows dots to be printed on the tape 50 times per second. The time interval between one dot and the second dot The time interval between one dot and the next dot is 1/50 or 0.02 seconds. But if we use a power supply of 60 Hz or 60 cycles per second, the time interval between the dots will be 1/60 or 0.01666 seconds. One end of the tape is attached to a moving object, in this case a trolley. As the object moves, it drags the tape through the ticker, thus leaving a trail of dots. This trail of dots provide a history of the object's motion and a representation of the object's speed and acceleration. Measuring speed and acceleration. The small distance between one dot and the next is the change of distance which the object has moved in the small time interval. So, by measuring the small change in distance, delta s, and knowing the time interval, delta t, for this distance, we can find the actual speed or instantaneous speed of the object at that particular moment of time. The instantaneous speed v is equal to change in s divided by change in t. The rate of change of velocity will be acceleration a, where a is equal to change in v divided by change in t. Reading the tape. If the distance between the dots is the same or constant with time, it means the object is moving with constant speed. If the distance between the dots decreases as the object moves, it means that the object is speeding up and the object is accelerating. But if the distance between the dots increases as the object moves, it means the object is slowing down or decelerating. Procedure. Part A. Measurement of speed. Steps to be followed. Attach paper tape to trolley and thread the tape through the ticker tape. Switch on the ticker timer and 1. Set the first trolley A in motion on the ramp to see that it moves with constant speed, so the distance between the dots of the ticker tape is the same. If it is not, then slightly adjust the incline of the ramp to compensate for the surface resistance of the ramp until you achieve the constant speed for the trolley A. 2. Now set the trolley A in motion to collide with trolley B. Both trolleys move together after the collision with slower speed. The ticker will record the motion. Note the spacing between the dots before and after the collision. 3. Cut the tape in two, where each section represents the motion before and after the collision. Use the tape to measure the speed of the trolley A before the collision and the trolleys A and B after collision. Table of results and calculations. To measure the speed of trolleys before and after the collision, examine the tape, measure the distance between the 10 dots on the tape before the collision and between the 10 dots on the tape after the collision. As the time interval between the two dots is 0.02 seconds, so the time interval between the 10 dots will be 0.02 s times 10 equals 0.2 s.